But what I wanted to say is I've switched things a little bit. So we'll have a lecture this morning owing to the request by some of the participants to learn a bit more on construction of composite vulnerability indices. We'll talk a bit about how we go about constructing indices in this vulnerability domain. And then what I'll do is we have a little exercise. So we're not going to call it a tutorial because I can't do that apparently, but it will be a lab exercise that you all can just do at the end of this particular lecture. And then what I want to do, and this is all providing I'm able to pull together all the data, is tomorrow I'd like to actually have data available for each of the states of India for us to just practice constructing an index together. So it would be a little bit of a tutorial. Now, for those of you who came and said, I really want to learn about climate mobility and we're gonna miss out, you're not missing out on anything. There was one lecture tomorrow on urbanization, vulnerability in urbanization, which frankly, I had not yet prepared, and I didn't have a lot more to say about the topic than what I said on Tuesday. I think this will be a more fruitful use of our time. So what we're going to do is we're going to move the theory, migration theory, and climate mobility lecture to right after this one. Tomorrow, you'll have 2 lectures on climate mobility first thing in the morning. Okay, one is going to. I don't know what's going on. Maybe it's battery or. Perfect. So to continue that, tomorrow 2 lectures, one on literature review around climate mobility and migration, a second one on quantitative modeling approaches. So you're not going to miss out on anything. I'm just adding some content that I think will be valuable for you. The tools that we'll be using for index construction is nothing more than Excel or Google Sheets. So we're not doing anything fancy. If you prefer to use something like R or Python or Stata or SPSS, you're welcome to do that. Does this make sense? Everybody on board? Okay. So let's go ahead and get started on this topic. One thing I wanted to do is go back to yesterday's lecture about vulnerability mapping. So I went through very rapid fire the approach that we took for Mali, the country in West Africa. And at the end, someone came up to me and said, well, could you clarify this one point about the steps that you took? And so I felt it would be better if I just laid out the diagram that we use for the vulnerability mapping. All of this is available in the step-by-step guide, which is also in the list of reading materials that you have. So you can, look on that list of reading materials, the content guide. It may even be, I'm not sure if it was downloaded or not, but it may even be on the drive right now. And so we laid out everything in there in much more detail. But, I mentioned some of the yesterday about identifying the framework, identifying, what you're going to include, what you're not going to include, the resolution of the data, the audience, et cetera. And then we had to choose the data layers. And we're going to talk more about choosing data in this lecture today. So you'll hear more about that. Then we process the data layers. So I mentioned, that some of the data came in the form of points, some came in polygons, some came in raster grids. So if the raster grids were too coarse, we had to resample and go down, the native resolution remained the same, but we had to resample so that everything was basically in a consistent 30 arc second or 1 kilometer grid resolution in raster format. So this was a conversion process here. We got everything in the grid format and identified the statistical, I'm skipping because the arrows point here. So what we did is we created a fishnet. This is a standard GIS technique where you essentially get, for that raster, you get the centroids for every grid cell. So you can convert in GIS, it's very easy to convert from raster to points, okay? So you get a fishnet of points, each with a unique ID. The reason you want to do that, and I'll show you later, is basically you want to do some of the processing in statistical software, not in ArcGIS. It's just a lot easier to do a lot of these steps in another tool. So then, each with a unique ID coincident with the centroid of each raster. Use extract values to points tool to transfer raster values to the point attribute table. Okay, so you have points. To get the values for each point, you need to transfer from the raster layer, which has precipitation levels, or it might have education levels, or it might have some other value. Mother's maternal education was one of the values I mentioned. Household wealth was another indicator that I mentioned. So you transfer from the raster to the points. Once you have everything in a points, you can basically convert it into a CSV, a comma-separated value file. It's essentially an Excel sheet, a tabular sheet, which you can then process in any tool. We list R here, but you could use it in Python. You could use it in Stata, SPSS, etc. Each one may have different limits, though, in terms of the number of values. So if you have a really large, like global raster data set at 1 kilometer resolution, there may be limits in even Excel to the number of rows and columns that you can have. They've changed a lot of those limits over recently, but in the past, limits. Step 9. Am I doing something wrong? You changed the batteries. Okay, changing it again. Perfect. All right. That also gave me time to get my timer going. So step 9, we do the transformations to the data, basically trimming the tails, logging values where there may be skewness in the values, things of that sort. And then we calculate all the indicators on a 0 to 100 scale. So that's a transformation step where all the indicators are done, calculated on a min-max transformation, which I'll talk about in a moment. Then in R, we calculate the sub-indices for exposure, sensitivity, and adaptive capacity. So each of these, once you've transformed the data to a 0-100 scale, which is a unitless scale, you can then basically aggregate them into sub-indices within the overall index. Then in R, we calculate the overall vulnerability index using the components. We also ran the principal components analysis. Finally, you want to see what all this looks like at the end of the day, right? So you need to join the tabular outputs to the centroid layer and then use the point to raster tool. So that's going back from, instead of going from rasters to points, you're going from points to rasters. And once you've done that, you can basically use the grids in ArcGIS or any other QGIS or any other tool to basically map out the results. Hopefully that's clear. What did I do with the clicker? And then at the same time, importantly, you want to make sure that you document all the steps you took. So what's easy to do is start playing around with the data and doing this and doing that. And then you move on to the next indicator and the next indicator. And before you know it, you forgot what you did to the first indicator. Now, if it's all scripted in R or something like that, you can go back to your scripts and see what you did. But in some tools like SPSS, you may not have a breadcrumb to show you exactly what processing steps you took. So these are some things that are important to remember. Okay, so today we're going to talk about developing a composite indicator or index. And this is the reference tool book that I use, and I think a lot of others use when they teach about the topic of composite indicators. So I just commend it to you. If you don't have it, you can download it. I'm going to be using elements of this today in this step-by-step processing that I'm going to discuss. So we'll jump right in. The outline today is step-by-step instructions, and then we're going to do a little exercise with Human Development Index data to see how two different types of aggregation methods change results. So here are the step-by-step instructions. We've already talked a bit about theoretical framing. So in the vulnerability space, you know, we've already seen two different framings. One is the original IPCC AR4 framing, and the second is the IPCC AR5 framing of risk. And so this would be largely, for the most part, what we would use in this context for vulnerability mapping, but you could choose another framework if you wanted to, and I'll show you what I mean by frameworks. Why is it needed? Okay, for part of the reason it's needed is, you know, I was talking about causal diagramming. So you want to know how the variables are related to one another in a kind of more systemic approach. And so the theoretical framework should enable you to be able to describe that. These are very common early frameworks that were used in the sustainability space, in the space of developing composite indicators of sustainability, which was basically state pressure state response, PSR. Pressure meaning emissions per capita, state meaning the level of CO2 in the atmosphere, response meaning government makes some policy decision and they decide to limit emissions. Then people, you know, started talking about, well, instead of pressure, maybe we should talk about driving force. Driving force would be population numbers or total GDP per capita or some other number that basically reflects the driver behind those emissions. Does that make sense? So these are some framings. And then ultimately, they started getting a little bit more complicated yet again and started saying, well, driving force, the population and the GDP drives emissions, and emissions then derive the state of CO2 in the atmosphere, and then impact is the impact on the environment, and then response both affects driving forces. So you could have a population policy, you could have policy related to emissions that says you simply can't emit as much, or you have to adopt, like if it were air pollution and not carbon dioxide, you could have smokestack scrubbers or something like that that would remove SO2 or sulfur dioxide from the emissions. So these would be policies that would affect overall the state of the system. So that's what I mean by having a framework is basically the same thing as I was talking about earlier. You want to know how these things are more or less related to one another. I'll skip the language up here. It's all there for you to read. But so this, again, the theoretical framework, it's a theoretical framing of how things fit together. Individual indicators should be closely aligned with the main areas. So if you have components like exposure, vulnerability, adaptive capacity, you should try to fit the variables into the proper bins. They should be theoretically related to that topic. The framework should also say something about how the aggregation occurs. For example, nesting of the index, components and indicators, and possibly something about the weighting. So, you know, you could just take all those individual indicators and aggregate them right up into an overall index without binning them into separate components. But you'd need to have a good justification for doing that and some rationale. So let's take a look a little bit further. This is, you know, from another reading, which is really helpful, by Niemeyer and Groot. And basically, it says, in a causal chain, social and economic developments are considered driving forces that exert pressure on the environment, leading to changes in the state of the environment. In turn, these changes lead to impacts on human health, ecological systems, and materials that may elicit a societal response. And so that feeds back. And so this is an example of a driving force mineral fertilizer prices, market demand for fertilizer, etc. Then you have the pressure, which is the use of mineral fertilizers, meaning nitrogen, phosphorus, potassium, which then can have an impact on the water and soil quality. And so you could have eutrophication of water bodies, which then might lead to algae and other problems in water bodies, lower dissolved oxygen, et cetera, lower transparency. And so the response might then be to say, well, we're not going to allow chemical fertilizer application at that level. That could be the policy response. That's just another concrete example of that, what we would call DPSIR framework. But other frameworks that we see are, examples here. One is, I would, say, might be a loosely coupled system in the sense that we expect these things to go hand in hand with one another to some degree, right? There's some systemic elements here, but it's not really a true system in the way we described systems the other day. This, I would say, is much more the toolbox approach, right? It's still, there are relations among these indicators, right? But the SDGs kind of explicitly just developed a large number of independent. And if you've looked at the indicators, there's, I think, 150 or 200 or more, maybe it's 200 plus. So it's really a long list of SDG indicators. And yeah, they're related to one another in one way or another, but there's not really a theoretical framing behind this. It was more that every UN agency in every country had certain agendas, and they wanted to be sure that their agenda was represented somewhere here in the SDG framing. Is everyone familiar with the SDGs? I see nods. In the US, people are largely ignorant of the SDGs. It's pretty sad. It's true. They just don't really pay attention to it, but they're really incredibly important. So here's an example of a framing in the vulnerability mapping or vulnerability index construction realm. And this is a framing which basically says you have sensitivity and exposure that leads to impact across 4 different dimensions: physical dimensions, social dimensions, environmental dimensions, and economic dimensions. I believe this was, particular example comes from a flood vulnerability mapping exercise in Germany, in a part of Germany. So they then summarized all of the total impacts across these 4 dimensions. And then they had a generic sort of adaptive capacity measure for each unit of analysis. And that led to an overall vulnerability metric. But they took here the geometric mean of these 2 variables. And we're going to talk more about what a geometric mean does and why it's useful in some cases to use a geometric rather than an arithmetic mean. I think everybody here knows what an arithmetic mean is. You add up all the values and you divide by the number of units and you basically get a mean, right? And then you can calculate things like standard deviation and stuff like that from there. So what we have here is basically, these diagrams are maybe not all that terribly helpful, but essentially, you can measure on 3 axes what's going on. You have the total impact, which is high, bad, or low, good. You have low to high sensitivity, and you have low to high exposure. And so, your ideal state would be to be somewhere down here in this corner. But if you use a geometric mean, it actually stretches the values in a different way. And you'll see that you get fewer low impact values, okay? The lowest impact value here is something like negative 0.5. Here it's like maybe negative 0.25 or something like that, or maybe even 0. So we'll explain in a bit why you get a lower impact value, or that the threshold for lower threshold for impact values is higher in a geometric mean. One thing I liked about the way this group did their vulnerability mapping was instead of the adaptive capacity element was not incorporated explicitly in the index. Remember I talked about how adaptive capacity could be used as a divisor, or you might subtract adaptive capacity from your overall vulnerability. in one of the slides the other day. So what that meant essentially, adaptive capacity sort of subtracts from vulnerability at some level. And so these adaptive capacities, in this case, the way they did it was they increased opacity. So you have total impacts from floods in this particular area of Germany, in red being the highest. But if there was high adaptive capacity, the opacity level increases, meaning that they kind of white out the area. Meaning you shouldn't be as concerned about the vulnerability in those areas because they have very high adaptive capacity. So it's sort of like subtracting out the vulnerability. All right, have I got everyone following so far? We'll see. Hopefully it will make sense to you. So this is a really critical stage where you're making decisions about what is in and what is out of your index. And of course, some of it's going to be just constrained by whether you have access to the data or not, whether they're available data. The OECD handbook says it should be based on analytical soundness, measurability, country coverage, and relevance of the indicators to the phenomenon being measured and the relationship to one another. The use of proxy variables should be considered when data are scarce. So proxy variables are variables that basically are, might be, what would be so a proxy for whether you live in a really rainy country or not might be a number of umbrellas per household. Or something like that. It's a silly indicator in a way, but if you obviously if you live in a really wet climate, you're going to have more umbrellas, and so that would be a proxy. So you want to check the quality of the data, discuss the strengths and weaknesses of each data set. Individual indicators should be closely aligned with the main areas of the components of the index. I already kind of mentioned this. And yesterday I talked about how for the vulnerability mapping we did in Mali, we provided justification for every single indicator saying this is how it's related to the concept that we're trying to measure. Where data are scarce, be clear about the trade-offs of using proxies, and a good practice is to list ideal indicators that would be used, thereby suggesting. So one thing we've done I mentioned earlier that I've been involved since the very start with Yale University. We've been working together since basically 1999, 2000, in releasing a series of indices called the ESI and the EPI. And one of the things that, because they're global indices and because they were, at first they were released at the World Economic Forum in Davos, so it got a lot of policy attention, and you'd have ministers of environment, and you'd have prime ministers there. And they didn't like it sometimes when their country was listed low or high. So we can talk a little bit about policy, capturing policy attention as well, and that's a few steps down the road. But one of the things that I would say is that we always try to list those data, areas of environmental data globally that really are lagging behind. And in some cases, we've had some success in improving data. And examples that I would say is that in the early days, in the Environmental Sustainability Index, which we published up until 2005, it was kind of a giant big basket of a lot of indicators, and it was a really interesting exercise. But frankly, it was not always tied to what countries are doing and their performance on the ground. What are the policies and whether they're actually implementing those policies and making things better. So we changed to this new framework called the Environmental Performance Index, which was much more geared towards what we perceive to be the need of policymakers, which is to know how are you doing on these critical things like biodiversity protection, climate mitigation, human health related to the environment, natural resource management. And so we did that shift. And when we moved to the EPI, instead of being takers and not makers, meaning we basically could only compile for the ESI those data that were already publicly available globally. And we would pull from the World Bank, we'd pull from the World Resources Institute, we pulled from other sources. And starting in the EPI, we started regularly holding expert group meetings to try to find out where the science was moving in different areas. We commissioned papers by experts. We then held workshops on air quality in Seoul, South Korea, another one on water indicators related to in Stockholm. Actually, it was at the Stockholm Royal Society for Royal, whatever they call it, the equivalent of the National Academy of Sciences there. And so we had this, so for example, out of this meeting, we developed an indicator on wastewater treatment that then became sort of the template for the SDG indicator that was later adopted. So we began to move the space a bit in terms of data production. This is an example. It's very messy, but you can see sort of behind the scenes the sausage making process when we were developing the Environmental Performance Index. And what it shows is basically where we were looking for data on different topics and whether or not we, decided to move forward or not, and the date by which we expected to be able to get all the data together. So for every year that we produce the EPI, there's some kind of sheet like this where we basically track whether or not we feel that we can move forward with a particular indicator or not. One of the notes here is that the data on nitrogen balance and the nitrogen use efficiency, which relates to agricultural chemical use, we found them to be too noisy. We analyzed the data, we looked at their distribution, and we were worried about it being too noisy. Other ones like species ranges, globally and nationally, they need to be refined. They weren't ready for prime time. So anyway, you get an idea of the kind of way that we went about as a team, looking at individual data sets and evaluating their fitness for the EPI. This is an example of a finished product, the EPI in 2016, where we had basically descriptors for every single data set and a justification for why they were included. All right, step 3, imputation of the data. This is something I'm not going to go into here, but what you find is when you have a matrix of countries and values for something. Now, I'm going to just take the example of freshwater quality. In the early days of the Environmental Sustainability Index, we actually made a really heroic effort to develop something called the Water Quality Index, which was a subcomponent of our overall ESI. And what we did is we basically took the best available data from UNEP GEMS, which is the Global Environmental Monitoring System, and then European Environment Agency and a few other country sources that measured like 5 or 6 different metrics: electrical conductivity, dissolved oxygen, I think, what's the other terms that they had? Turbidity or levels of gunk in the water, things like this. And what we found was there were just huge gaps in a certain country, and some countries didn't have values at all. So we needed to basically, in some cases, fill in individual gaps for the subcomponents of the Water Quality Index. And then for some countries, we simply didn't have data. So we used something called Monte Carlo multiple imputation method, which basically identified a number of correlates for water quality, and we're using national level indicators, and then imputed the values for those countries for which we didn't have values. So it's kind of a risky business, let me just tell you. But in some cases, you have to impute the data because there's these data gaps in the matrix. And there's whole methods for doing that. So we found that a lot of countries, like Taiwan, is not part of the UN. So we wanted to include Taiwan because it's a major economy, but it's not a UN member, so it doesn't report through the UN system. North Korea has very spotty data. So in some cases we had to impute. In some cases we decided to leave the country out because there's so many missing data. Another way, in some particular cases, if you had about 5 indicators in a particular subcomponent, what you could do is simply average around if you're missing one of those. So you simply delete that one value and average around it. I mentioned the MCMC, Markov chain Monte Carlo multiple imputation method was one of the approaches that we took for the water quality work. All right, let's look at multivariate analysis. This is where you've got all your raw data, and you have the raw variables like dissolved oxygen or particulate matter pollution levels, and you start analyzing the distribution. You check the underlying structure of the data along with two main dimensions, namely individual indicators and countries. You identify groups of indicators or groups of countries that are statistically similar and provide an interpretation of the results. And so you're starting to get into the data and explore them. Basic descriptive statistics are usually the starting point. You have, your min and max values, your means, your medians, your standard deviations. That's just the starting point. Then you want to look at the underlying relationships between the indicators. Then you want to see that the components are closely tied to levels of economic development in the case of EPI, or for our purposes, it would be closely tied to the concept of vulnerability. So one of the things that we found a lot is that we have in the environmental health sphere of our environmental performance. I'll have in a moment, I'm going to show you the structure of the Environmental Performance Index. But the environmental health sphere, that particular portion, that component of the EPI, a lot of the indicators are very coherent because they tend to have to do with levels of development. So things like air pollution levels, access to water and sanitation, lead exposure, all of those things tend to be pretty consistent with GDP. But in the environmental domain, you might have high deforestation rates, but low carbon dioxide emissions. You might have high offshore fishing rates of trawling levels, but you might be cutting all your forests down. So there's these elements in which, yes, they're all part of environmental, what we call ecosystem vitality, but they tend to be orthogonal to one another in certain countries. You're not always seeing the same patterns. Does that make sense? So these are some key points from the OECD handbook. Individual indicators are sometimes selected for substantive or theoretical reasons. It's because they're so closely tied to the issue. And they provide important information about vulnerability or sustainability, but what people tend to ignore when they develop indices is the statistical properties of each variable and how they relate to one another. So that's an important element, is making sure you understand how, because essentially, we'll see in a moment, but if one indicator is high in a component and the other, and they run in opposite directions from one another, what's going to happen? If deforestation is orthogonal to trawling, it neutralizes it. It becomes you go towards the mean of both variables. So that really doesn't help. That's what we call compensability. So you want to know what those relationships are. You're going to be assessing the suitability of the data, and this will inform later normalization, weighting, and aggregation. Let me see how we're doing on. Finally, one very useful approach that we talked a little bit about yesterday is principal components analysis. And here we want to reveal how the different variables change in relation to one another. Are they correlated highly? And if so, one valuable thing about PCs is that you can transform the set of variables that you have, the large set of variables, into a limited set, a smaller, reduced set of principal components, where the first principal component finds the greatest variance in your entire cloud of data, and it runs a line through that. And then the second one finds the next axis, which is orthogonal to the first one. And so that's a way of doing data reduction when you have a large pool of data. Okay, this is an example of just looking. Scatter plots are a very useful tool for just, most of this, you're probably familiar with from your statistics courses, but just looking at how these things are related. I mentioned earlier that environmental health is generally, countries tend to be pretty environmental health against the overall EPI score. The countries tend to be fairly, that tends to be highly correlated with GDP, but you see a lot more scatter in ecosystem vitality, meaning that the coherence of that particular component of the EPI is a lot less. There's a lot less coherence there. All right, normalization. This is an important step. What that means is that we can't just measure total deforestation in a country and then compare it to total deforestation. Total deforestation in Brazil is going to look a lot different than total deforestation in Tonga in the South Pacific, right? Brazil is a vast country. Now, you know, one important step is standardizing. So you could begin by just standardizing the values. And so some ways this is a two-step process. First, you want to figure out what the proper denominator is. So deforestation per unit area of the country or per unit area of forest cover, starting at some baseline, is one way of doing the normalization, or looking at total CO2 emissions divided either per capita or per GDP. One approach will look more at what's just in terms of equitable distribution of CO2 globally. The other one would look much more at whether countries have large or small economies and whether your emissions are relatively efficient related to the economy or not. So that's a sort of first step, is just standardizing. But then there's an additional issue in that each of these units is very different. So units of PM 2.5 are different from rates of deforestation, are different from CO2 efforts to measure or CO2 per capita. So you want to have everything on a common scale. A 0 to 1 or 0 to 100 scale is one of the common ways of doing that. You can also do something called a z-score, which is, if I remember, it's the mean minus the standard deviation divided by the mean. And basically that gives you a metric that shows how high or low you are relative to the mean in the distribution. So let's talk about standardization first. Here are some different ways that we've standardized in the EPI. So, you know, wastewater treatment, we look at the percent of wastewater treated weighted by the connection rate of the population to the wastewater treatment system. So it's great if 50% of your wastewater is treated, but if only 2% of your households are actually connected to any kind of sewage system, that would reduce that overall wastewater treatment metric quite substantially. Nitrogen, you know, each of these has a different kind of denominator or normalization, standardization metric that allows them to be compared to one another, countries to be compared across one another. All right, normalization methods are varied. The simplest method is basically ranking. So that if you have extreme outliers and you just rank your values from 1 to, let's say there's 200 countries in the world, I'll just say for example, then every country gets a rank value, and then you can rank every single indicator and basically use the average ranking as a way of constructing an index. It's not a very elegant way, but it does eliminate the problem of outliers. Standardization or z-scores is what I mentioned before, and basically one of the ways this can be useful, but one of the issues is that if you have really extreme values for some of your indicators, then those will disproportionately influence. So if you're averaging z-scores across multiple variables in an indicator or a subcomponent of your index, the one that has the greatest distribution, the widest spread, is going to have the greatest impact on your overall score. It's just a statistical property of the data. But it doesn't necessarily mean, just because that one indicator has a wider spread, that that's the most theoretically important indicator. So it's essentially, if you just threw them all together and use them without questioning, you would essentially be biasing your index in some way by including these variables that have very different statistical properties in a common component. Min-max is the one that we're probably going to focus on the most for this particular portion, and that's basically looking at transformation on a 0 to 1 or 0 to 100 score. And so one of the things that's often important in min-max transformation is to do a logarithmic transformation first. And that means that extreme values are less likely to kind of affect your overall component index scores. It rewards. So one of the other properties of logarithmic transformation is for some areas it may be easier to incrementally make an improvement when you're at a very low level of performance. Let's say for waste, let's just talk about water and sanitation. So percentage of households with sanitation. It may be easier to get from, say, 10 to 20% of your population that has adequate sanitation than it is to get from 90 to 100%. Because those early gains may be a lot easier to achieve. So one of the things that logarithmic transformation allows you to do is kind of take into account the fact that early gains at a low level of performance are easier than when you start getting to a much, it's a lot easier to reduce mortality by 1% at a low level of performance than it is when you get up to the point where your mortality is very, very low. I don't know if I've made that clear or not, but that's one reason from a substantive perspective and not just a purely statistical perspective that you would want to do a logarithmic transformation. Yesterday, I also spoke about trimming the tails. So when you have extreme values, the first thing you want to do is basically trim the tails. Then you want to do the logarithmic transformation. You can also just do a basic distance to reference, and this is calculated as the ratio of the country value to the target. So that could be one way that you might choose to do it. And the other is to create categorical variables. So basically, if you're between this value and this value, you get a 1. If you are between this value and this value, you get a 2, and then you go up to 5, and you have 5 categories, and 5 being the best. So that's one way, that you can look at these variables and these numbers is basically giving things like you fully achieved, partially achieved, etc. The goal. Step 6 is weighting and aggregation. This is where this is a subjective element as well. Each step involves some subjective decisions, but I think this is the one that tends to come in for the greatest criticism when you're creating composite indices, because you're basically making a lot of judgment calls about the relative value or importance of each indicator in your framework. Let's take a look here. There are different rationales for different weights among indicators. You could have theoretical reasons. So some of those indicators that are in a particular subcomponent might be more closely related to the topic that you're really interested in. Theoretically, you could have, in a deforestation indicator, you could have one indicator which is essentially the actual rate of deforestation, and another which is the, possession of chainsaws per capita or something like that. Well, obviously you'd want to measure and weight the variable that has to do with deforestation more than you use, this is an absurd example, but chainsaws per capita, would be a much poorer proxy for that measurement. Expert opinion, that's why we convene those expert groups. You would have a group get together and say, some things are more important than others, and you basically rely on that expert opinion. Salience in policy circles. I mentioned yesterday how some things are on the political agenda much more than others, so you might want to weight those more importantly. For many years, we did not break out climate change as a separate component of the EPI. You know, back in the late 2000s, climate was important, but it wasn't necessarily as important as it was in the last decade. And so when we started developing the EPI, the climate element was part of the overall ecosystem vitality portion. And we broke that out and made it a separate component when it became more and more salient. Data quality, you might want to weight some indicators more than others because the data are just of higher quality. The credibility of the source, I talked a bit about that yesterday, and then statistical reasons. One indicator could simply offset another, as I mentioned, the compensability factor. So if you downweight one of those indicators, it's less likely to compensate for, you know, a low score in that indicator is less likely to compensate for a high score in the other indicator. And then there are different approaches to aggregation, which have different properties in terms of the way they affect. So the linear arithmetic mean of indicators assumes a linear relationship among the indicators. So what we kind of assume, it's implicit, we don't go spelling it out in in a lot of detail, but we basically assume that if you go from with 100 being the high score on the EPI, if you go from 50 to 60 on the forest indicator, it's roughly the same as going from 50 to 60 on the carbon intensity indicator, the carbon CO2 per GDP measure. And so we're assuming some kind of linear relationship. Geometric multiply scores of n indicators and take the nth root of the product. The indicator with the lowest score has a disproportionate impact on the aggregate score. So this is one way of basically saying if you consider all of your components to be really important, and you want to address the issue of compensability, then you shouldn't allow high education to sort of offset something like infant mortality rates, where infant mortality rates are really bad. So if you want to do that, one way of doing it is to take a geometric mean, and that basically means that if you score poorly on infant mortality, it's going to have a greater impact on, it's going to bring your score down, your overall index score down a lot more. I think that's spelled out pretty clearly. And then in a multi-criteria method, there's no solution optimizing all the criteria at the same time, and therefore compromise solutions have to be found. Information contained in the impact index, which is useful for solving the so-called multi-criterion problem, is intensity of preference, number of criteria, weight, etc. I've seen multi-criteria indices developed. What I will say is they're often harder to communicate to policy audiences, so there's some issues with that in terms of being able to communicate the results. So as I mentioned earlier, the arithmetic mean linear aggregation, which is very commonly used, assumes that there's a linear form that basically increases of the same unit increase across a variable basically results in improvements in either sustainability or reductions in vulnerability that are kind of linear in nature. So it doesn't really address the fact that there might be threshold effects, that beyond a certain point of CO2 emissions, you might start getting catastrophic impacts, or if your SO2 emissions are a certain level, you might, or carbon monoxide emissions, you might, beyond a certain threshold, irreversibly impact people's health. So you need to think about that there may be, in some cases, in some indicators, thresholds beyond which the harm is a lot greater than if just incremental linear increase would suggest. So this one does not allow for absolute unsustainability. So, basically another element of the problem with linear aggregation is that if there is like one variable that really is the most important variable, it might not really come out in a kind of linear aggregation approach. I talked about compensability, And then double counting is another issue, that if several indicators are highly correlated, then that could create certain issues. For the EPI, we try to be very transparent about the weighting that we use. So this is one formulation that we use for weighting. Note that back in 2018, we were still including climate and energy as a part of this overall ecosystem vitality. And each of these shadings shows what kind of fraction of the overall subcomponent went into that component. So, the ecosystem vitality is made up of 0.05 agriculture, one unit of sustainable nitrogen management, et cetera. Here you see, I think, a slightly more intuitive approach to showing the weighting scheme. This is the 2022 EPI. You can see now climate change is separated out as its own indicator, with largely related to CO2 emissions, but including some land cover change metrics. Then we have all the ecosystem vitality, environmental health. And each one of these then has a wedge that shows the percentage contribution to the overall EPI. Uncertainty and sensitivity analysis is an important later step. I mentioned in the Mali case that we did some sensitivity analysis where we moved from a weighting scheme that we had proposed based on the importance of certain indicators to an equal weighting scheme. And so this is just an example of doing the same thing for tabular data using country level scores. And they basically looked at the change in ranks of the ESI in 2005 according to different weighting schemes and different aggregation schemes. And one of the things that I'll just point out is that for high-performing countries, Finland, Norway, et cetera, they're very high-ranked, so in the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Depending on the different aggregation schemes and the different weightings, you didn't see a lot of variation in ranks. Guyana is the first country on the list to have a fairly high variation. And also at the low end, North Korea, Taiwan, et cetera, you don't see a lot of variation in the ranks. Where the variation comes in, it tends to be much more in the middle ranking countries, where these assumptions the assumptions on how you're constructing your index can have a lot of influence on the overall index score. Finally, you want to do data analysis, double check, the different components, the relationship among the components. This is where we often say to users of the EPI, don't just look at the overall EPI score or the rank of the country as your metric, but you really should drill down underneath and understand, like for the United States, how these different components interrelate with one another. And how, U.S., for instance, is doing very poorly on forests. It's ranked 115th in that case, but we are doing generally pretty well on air quality and water resource and management. So these are things that we encourage people to do. And then finally, you might want to look at the links to other indicators such as GDP. So this is a correlation of the ESI, the earlier Environmental Sustainability Index related to GDP. And again, you can see some countries are doing better than what might be expected based on their GDP levels, and some are doing worse, like Taiwan, Turkmenistan, I guess that's Belarus. Even the US is doing more poorly than its GDP would suggest. This is an example of the ecological footprint I mentioned the other day, which is hectares of biologically productive land per capita. One thing I'll just point out is that the ESI sort of is an inverse of the ecological footprint. So a lot of countries that do high on the ESI scores also have really bad ecological footprints, with this being a bad area over on this side. Finally, you might want to do different types of data visualization. So this is the SDG index kind of dashboard. They also have whether you're improving or declining in terms of time series data. So it gives you an idea whether countries are doing better or worse. One thing I always find interesting is that we're doing pretty well on poverty with a lot more green and yellow over here. But for things like responsible consumption and production, climate action, and I don't know, partnerships for the goals, it's not as good. A lot of red. And then this is an example of a kind of complicated visualization, which I don't actually find all that terribly useful, but because I don't know why you want to bend your bars in that way. But it doesn't give additional information. But it's an example that someone thought, well, we should do this as a circle rather than a straight up bars. But it shows that certain countries are doing better on gender inequality than others, with Europe and Central Asia doing really well and South Asia doing kind of not so well and Sub-Saharan Africa doing much worse. These are some other ways of visualizing using, these kind of not quite spider charts, but using equivalent to spider charts. There's another, example of data viz from the Global Risk Report with a lot of these in the climate area, and then we have other ways of visualizing. This is how we did things with the EPI, so you could look at each country and analyze its results. So there's a lot more to say about this than I can convey in one lecture, but this gives you an overview of some of the steps for constructing metrics. It's not a linear process necessarily, so you find yourself going back to the drawing board, I should say, not the dashboard, the drawing board at certain points to do this. And some steps are more critical than others in terms of the overall influence on the overall vulnerability index or the so what I wanted to do is take a few minutes. Let's see, what time are we at now? 11, and we have until about 11:30, right? Yeah, so what I can do is answer some questions if there are questions that arose from my lecture just now. And then I wanted to do a little exercise where you might have to bring out your laptops and download a spreadsheet that's already available to you on the Google Drive under tutorial 3, we're calling it. Double check the Google Drive if you don't mind. And I can also bring up the spreadsheet to describe what we're going to do with that in a moment. But I did want to check to see if there's any questions. I know I went through that very, very rapidly, so I'm happy to answer any questions. Sorry, I need to give you the mic.
Thank you, Alex, for another brainstorming session. My point of query is that, so for example, we as usually as a geographer went to fields, and in many cases, like issues like Sundarban, we need to ask questions which gives us result in binary terms, yes or no. Now, what to do with this binary data if we are considering to put them into the environmental quality index?
Yeah, that's an interesting problem. I guess I presume in some cases you might have multiple yes or no's. So then you could start looking at the relationship among the responses and maybe aggregate up responses across 3 or 4. But can you give me an example of a yes or no type question you might ask someone in the Sundarban?
Say, for example, if we go to a household and just ask them whether they have a gas-based oven or not, whether they use rudimentary form of cooking system, they will come up yes or no. We have a gas based oven, or no, we don't have any gas based. That will give us a sense of indoor environment within which they are living, and that can be put as an indicator for our environmental performance.
I would say that that could be used among a number of different household level variables that could, so you might be collecting data on things like if they're not using gas, then are they using, animal dung, or they are using, wood, mangrove wood, or some other wood source, or charcoal. And each one might have a different sort of potential harm to the population. Indoor air pollution is clearly one of the huge issues, particularly among women, for their health. So I think you might want to go beyond just that binary question, ask more questions. If all you were able to ask is that one question, then it could be combined with maybe a number of other metrics into something. I have to give it some more thought. It's a good question. Are there other questions related to today's lecture? Yeah, another question.
For imputation purpose, you have used MCMC model, that is Markov chain Monte Carlo multi-imputation. So if you look into the Markov chain model itself, it looks into the past data, present data to predict the future data. Now, if we do not have the past and past data, then how this model is going to work?
I think the MCMC method can be used in a number of different ways. I actually have some separate slides on the MCMC method, but I don't have them right with me here. And this is not a particular area of expertise. I tended to work with a statistician who worked with the model a lot more. My understanding is it can also be used so it generates multiple variants and using a number of data inputs. And I was under the impression it could also use correlates. But I'm going to have to go back to my slide deck and then talk to you offline about that, because it's a great question, but I don't have the answer. So I realized today's lecture was a little bit more technical in nature and maybe not as much, conducive to large discussion. But I did want to get it in, and tomorrow what we can do, I want to pull together some data and we can actually start working together in sort of developing, some kind of index framework on a state level. My hope is to do that for India. But today what I wanted to do is look at the implications of using arithmetic mean versus geometric mean for the HDI. So I put, hello? It's in the Google Drive, yeah. So there, in a lab, I think it's tutorial 3 folder on the Google Drive, you'll find a spreadsheet. And it's a Google sheet. Hopefully if you have your laptop here, you can pull it up. And I'll bring it up. I guess the best way is for me to bring it up here and describe a little bit. So what? Let's see if that's all right. He's bringing it up here. So this is a relatively simple exercise, but what I want you to do is, sorry. I'd like you to, yeah, just maybe if you hold that for me. So I want you to calculate, first of all, the geometric mean of these indicators. And there's the three indicators that need to be averaged or from which you need to calculate the geometric mean are life expectancy, the education, which is the average of expected years of schooling and the mean years of schooling, and then finally the GNI, the gross national product or income per capita. And so this basically is a function of these indicators. Wait, these indicators multiplied times each other. And then you take the cube root of that. So the cube root is like this. And I'm hoping this works. And so then you can calculate that and pull it all the way down. And then the arithmetic mean here is these three indicators added together and divided by 3. Then what I'd like you to do is sort and come up with the geometric mean rank. Sort again, so you would sort here. So just so everyone's on the same page, hopefully you can see that, but if it's not big enough, I'm not sure I can make it any bigger. You've got the formula for calculating the geometric mean, and hopefully you all know the formula for calculating a normal mean, where you're basically adding the indicators together and dividing by 3. And then sort on the geometric mean ranking. So from highest to lowest. So if you can just. And you can sort on the arithmetic mean ranking from highest to lowest. And then you can look at the difference in rank. So here I'll take equals the arithmetic mean minus the geometric mean. So what this allows you to do then is look at how scores change up or down based on whether you take the geometric mean or the arithmetic mean. And maybe we can take a look at that in a second. Have most of you been able to follow the steps thus far? Not terribly complicated, right? And if you're having difficulty, let me know. I can come by, or maybe you can turn to a neighbor and ask them about it. Yes. What's that? Do the steps. What I'll do is I'll show you the formulas again. So again, the geometric mean is basically, if you click on this, you'll see what it does. So it takes these three scores, right? The life expectancy, the education, and the GNI per capita. And then you take the cube root. That's the way in Excel of doing the cube root of the value of the product of those three variables. And that produces the value here in this column. Then the same is true for the arithmetic mean. All you do is oops. You're basically adding the three values together and dividing by 3. So so that's the average value, and here's the rank arithmetically. So what you see is that the original HDI does use it does use a geometric mean. And so what we're doing is comparing it to an arithmetic mean of the three values that go into the Human Development Index. So what I did after I calculated in this cell, I simply pulled that formula down all the way to the bottom. And I did the same here. I pulled the formula all the way down to the bottom. Then I sorted on the scores. And when I sorted on the scores, I was able to then add a rank 1, 2, 3, 4, 5, and I pulled those numbers down. So that's how, those are the steps that I took to get these. So let's take a look now at some of the differences in ranks. Just 1 second, sorry, there seems to be something missing. Yeah, so the difference in rank is basically I think I did the arithmetic mean minus the geometric mean. Let me double check on that, sorry. What's that? So Pakistan has the highest difference. Okay, let me see if that's true in my. So I subtracted the arithmetic mean. Let me do it in the other way around. The geometric mean from the arithmetic mean. Wait a second. Just 1 second. So this is the subtract the geometric mean from arithmetic mean. I want to do it the other way around. So I'm going to do the arithmetic mean. Oops. Yeah. So if you do the subtraction in the other direction, you're finding that Pakistan comes out with a difference in rank of 7, is basically showing that if you take the arithmetic mean, Pakistan actually shows up better than it would have shown up under a geometric mean. And than it does in fact show up in a geometric mean. So that means that for one of these performance indicators here, Pakistan is lagging substantially, and it seems to be the education indicator. Okay, so that's one reason why the HDI uses a geometric mean, is to basically bring down the overall score of some countries where there's very high, uneven performance across the components. Some countries actually would benefit more from an arithmetic mean. In those countries, well, I think Pakistan is a classic case, but there's others here. So a number of countries benefit from arithmetic mean. All of them tend to have relatively uneven levels across the 3 indicators. So what you want to do, why the HDI chose the geometric mean, in summary, is basically to penalize countries if they perform poorly, particularly poorly on one of those indicators, just to say. So that kind of, I think that brings us to the end of that particular exercise. What I'm hoping is that tomorrow we can spend a little time actually playing with real data and doing a bit more of this in class. And I can talk also a little bit more on, construction of vulnerability indicators at that time. Are there any other questions or issues, concerns? How to rank them? All I did was I basically sorted on the scores. So I'll just show you once again. If you hold my shoes. So what I did was I took the largest to the smallest score for HDI, and then I'll just delete these values. Yeah, well, oops, I just hit the wrong one. All right. So I then just I added 1 and I added a 2. And then Excel has a handy feature where if you just pull that down, it will just continue the ranking all the way down to 193. That makes sense? And you can do the same then if you sort for the arithmetic mean on largest to smallest, you can do the same process. So one of the steps that I did not cover in this particular exercise, and it's worth just exploring, is how they calculate the score for life expectancy to begin with. This is basically a min-max score. So let me just move over in the spreadsheet. What does this min-max score tell you? It basically says, you can just interpret by looking at this here, that the lowest score for life expectancy at birth is 20 years. I'm actually curious to know now which country it is, but we'll look at that in a second. But the highest score for life expectancy is 85 years. A min-max score is calculated as follows. You take the country score minus the lowest score in the range of all countries. So that lowest life expectancy is 20 years somewhere in the world. I'm not sure where. It might be Haiti or Niger or someplace like that. Then you divide that by the difference between the highest in the total range of scores for all countries and the lowest score, 20. Does that make sense? So basically, the score for Liechtenstein in this case is Liechtenstein score minus 20 divided by the total range, meaning the highest score for all countries minus the lowest score for all countries. And let's see where that country is that has a score of 20. There's no 20? Yeah, I wonder why they chose 20. This is basically coming right. What's that? Yeah, so I don't know why they chose 20. You could choose an arbitrarily low value, and that appears to be what they did. They chose an arbitrarily low value. Let's take a look at, interesting, in India, your commas go in a different location than so I'm a little confused, but this looks like about 146,000 for a country, for Liechtenstein. So let's see how they did this one. So in this case, what they did is they took the log, and that's written up in their material and methods. So you have the raw value here for Liechtenstein of 146,000 GNI per capita. So they took the log of that value minus the log of 100, and then they took the log of the highest value minus the log of 100. And I'd have to look into their material and methods a little bit more. They have a very detailed methods document to understand a bit better why they use this methodology, and why the low value is 100. It may be that the lowest GNI is 100. I doubt that, but they also don't use necessarily the highest of all the GNIs. It might be the average of the entire series. Yeah, yeah. Um, 690 is the minimum. Yeah, yeah. Yeah, I remember actually when I went back to the documentation, it was all explained in greater details. So I can put the documentation in on the folder as well, because we got a little tripped up as well when we started doing this to recreate the HDI. So one thing I'll just say in general, if you want to learn about index construction, probably one of the best ways to do it is to go back to an already constructed index and figure out how they did it using the same formulas that they used and try to reproduce what they did. So it's a good first step in kind of learning the process of constructing an index, is just following the methodology that somebody else used and seeing if you can reproduce it or not. So this was I'm glad for some of the input of the participants here, because it's very helpful. So I think with that, maybe we'll break. If you want to talk to me about any specific issues, or if you're having problems still, we can, we're having tea now, so feel free to come up to me with your laptop, and I'll be happy to walk through any issues that you may be having. So thanks for that, and I don't know, where's the tea? Still in the oil. Yeah, so we're going back across the courtyard. Enjoying the nice weather today. It's a little breezy. It's sunny. The blue skies. I love it.